Hello, everyone. We have a number of people still joining, so let's give them a minute before we kick off this virtual meetup. All right, hi, my name is Jenny. I'm on the community team here at Docker, and today I am welcoming a dear friend, Elton Stoneman, to lead our virtual meetup. Elton is a Pluralsight author, a Microsoft MVP, and an architect at Docker. He is knowledgeable about a lot of things, and particularly Docker and ARM, and how to build multi-architecture applications with Buildx. We will be go ahead and put your questions in as they come up, but we'll be taking questions kind of at the end and opening up for discussion then. So Elton, please take it away.
Thank you very much. Thanks for joining, everyone. Hope this is going to be a useful session for you. So I'm based in the UK, so I'm on Docker's strategic alliances team. So we work with our partners like ARM and Microsoft and work together to find out how our tech fits nicely and what we can do to make people's lives better. If you're looking at the background and wondering what's going on, my office is in what used to be an old barn, and I'm only kind of partly converted it. So this is a minimum viable office, which is why there are bits of ceiling missing, but it's good enough for me. Okay, so that's enough about the office. So I'm going to talk about multi-arc images and specifically around ARM architectures. There's only really three things I'm going to cover. There's going to be a lot of demos. Hopefully this is going to be a session that's useful whether you're familiar with Docker but not familiar with ARM or vice versa. So that's what we're hoping to get to. So what I'm going to cover is really understanding what we call multi-arc images. So a Docker image that can work on different architectures. I'm going to lose the headphones, so I don't need it right now. That works on different architectures. So Windows, Linux, ARM, Intel. I'm going to show you how we used to do that. So you've been able to do this for a long time, but it's been a little bit awkward and a little bit clunky, but there are still certain certain things that are valuable about doing it the old way. So we'll spend a little bit of time walking through how I do this right now. And the big focus is on the new way of doing things, which is this new component of Docker called Buildx, which when you compare it to the old way is super simple and really straightforward and easy to use. So that's what it's going to be all about. There's a bunch of demos. All the code is on GitHub. It's all kind of open source. You only need Docker desktop to follow along at home. Mac or Linux, Mac or Windows is fine. And as Jenny said, any questions, put them in the webinar thing and we'll come to them at the end. Okay, so here we go. So the part of the whole premise of Docker is that you can package up your application in this thing called a Docker image that contains everything it needs. Contains the application runtime, contains your application, all its dependencies, configuration, everything you need to run. So when somebody comes along and does Docker container run and gives your image name, then it works the same everywhere. So it works the same on my laptop, on the data center, in the cloud. It's going to be the same everywhere. Now that story is not quite the consistent if those are different types of computers. So if I've got a Windows machine that I'm running as a developer and I'm pushing it to a Kubernetes cluster in the cloud that's all Linux, or if I want to try and push something out on an edge device that's running ARM instead of Intel, then it doesn't quite work in the same way. And the reason for that is when you package up this application to run in a container, when you build this thing called a Docker image, that image is actually specific to your computer architecture. So because the way that Docker works, because the way that a Docker container is so lightweight, because the application in the container runs directly on your hardware. So for that to work, the application image has to be baked to work with one specific CPU and one specific operating system. So what you actually get when you build your Docker image is your image is targeted for a specific OS and a specific architecture. And you can't just take an image that was built to run on Linux, on ARM, for a Raspberry Pi and run that on your Windows laptop. It just doesn't work. So instead, what people do is they build different images. So the same application can be packaged up in different ways for different architectures, and you end up with something a bit more like this. So I've got my app packaged to run for Linux on ARM64. So that would be the code name for an Intel x64 processor, which is the majority of what we've got in the data center and desktops and laptops. I can package up the same application to run on Linux on ARM, which would be 32-bit ARM, which is Raspberry Pis, or Linux on AMD 64, or ARM 64, or Windows AMD 64. So those are the kind of codes that we're dealing with. And the advantage of that is if your application is cross-platform, so you're writing your code in something which is portable, like Node.js or Python or Java or .NET Core, then you can build these separate packages and then anyone can kind of run your app. But they'd have to know about the different architectures and make sure they pull the right one. And that's where multi-architecture images come in, because what Docker has the ability to do with the Docker registry is to have a kind of umbrella image name. So I can have my application image, which is applicable to any of these architectures. And when a user pulls that image down to run a container, Docker pulls the right one. So if I run Docker container run on my Raspberry Pi, I'll get the Raspberry Pi ARM32 version. And if I run the same command with the same image name on my Windows 10 machine, then I'll get the Windows Intel version. So that's how multi-arch images work. So the reason why that's so valuable is it's mostly about the diversity of it. So if you think about being able to run the same application on any kind of hardware, then suddenly you can bring a lot more people into your project team. So you're not mandating that they have to have a Windows machine or a Mac or a Linux or anything like that. You're not mandating the CPU architecture. So suddenly you can be a lot more approachable to who's working on your project, and the setup becomes minimal. So you're just telling people, bring whatever computer you've got, install Docker, and you're ready to be part of the team. And then at runtime, that diversity gives you a lot of options that you don't otherwise have if you can only build something that runs on Intel on Linux. Because if you've got these multi-architecture images, you can take advantage of running them in kind of any cloud. ARM chips are in data centers in the Packet data center, and AWS recently released ARM instances. So you can go to AWS. You can spin up an A1 instance, which is the type of instances that are based on ARM CPUs, and they're almost half the price of an Intel machine, because the ARM processors are so much more efficient to run, then the clouds can pass on those efficiencies to you. So if you've got a portable app, being able to run it on an ARM processor in the cloud and have your infrastructure costs without any code changes is a pretty valuable proposition. And then the last one is things like Edge and IoT. So increasingly, the devices that are out in the wild are based on ARM processors, because that's the lightweight and efficient versions of getting the processing units. And being able to run applications in containers solves a lot of the distribution problems. So one of the big problems with IoT projects is once the devices are out there, they're gone. You have no control over them. And if you want to push an update to your application, typically that's done by packaging up a new bundle of the firmware, and then the device has to download that and effectively reflash itself. Whereas actually, if you can have your application running in containers on the device, then it's much simpler to distribute and deal with updates with a lot less downtime. Okay, and what that gets you is now you can do your Docker container run, and if there are multi-architecture image, then whichever machine you're running on, Docker will pull down the right flavor of that image and run your container, and then it will be the same experience for everyone. So there's a minimum requirement that whatever you're putting into the container has to be able to be packaged for ARM and Intel and Windows and Linux. But provided you have that, then you can get everything up and running really simply and make that super consumable for any type of user. Okay, so that's kind of enough talking for now. Let's go and have a look at some demos. So where are we here? So like I said, all the demos are on, oh, let's stop my presentation, because otherwise you won't see the demo. Okay, there we go. So all the demos that I'm going to do are all up on GitHub. Right at the end, I've got a slide which will tell you where to navigate to find them. You have to wait till the end to see that. What I'm going to do is just show you some examples of using a multi-arch image, and then later on we'll talk about how you build them, and then finally where Buildx comes in. So if I open a terminal here and run Docker version, so I'm running on Windows. I've got Windows is my Docker engine, which means I'm just running Windows containers. Docker version tells you about the command line that you're using, but I'm also pointing to my local Docker engine. So I've just got Docker desktop running. So I've got Windows containers here. Now, if I run what I know to be a multi-arch image, so I'm going to run this. It's a really simple application which just packages up a little script that tells you a little bit about the computer. This is from the book that I'm writing at the moment, so that all the examples in my book are all multi-arch images, which is why I'm using them today. So all this does is it tells you a little bit about the container runtime. So the container starts up, it tells you what the host name is, it tells you the operating system that it's running on, and the IP address of the container. It's all pretty simple stuff, doesn't do anything particularly interesting. But what I can do is if I inspect the image that I've just pulled, So I'd already pulled that image because I knew I'd be doing it. But if I hadn't, when I did the Docker run command, it would have pulled the image for me. And that's when Docker will say that the engine version is OS is Windows, architecture is AMD 64, and it will pull down the right flavor of the image. So the image that I have on my machine, if I do a Docker inspect, I get all this stuff coming out. And somewhere up here, I've got the architecture and the OS. And actually, there's another command that I can run, which would just pull out those bits, which is more interesting. So if I run this, Docker image inspect, and just tell it that I just want the OS and the architecture, then on this machine, on this Docker engine, that image, CH02, chapter 2, Hello Diamol, which is the name of the book, this is Windows AMD 64. Okay, so that's straightforward. What I can also do is I have a whole bunch of machines here that you can't see, which are, I've got Raspberry Pis, I've got Pine 64s, which are ARM64, I've got small chips which are running Intel, I've got a bunch, all in a Docker swarm, and I've got a bunch of scripts that I can use to switch between them. So if I switch my Docker engine to my Raspberry Pi, now I run Docker version. I've still got the same client because I haven't changed the client that I'm using, but now I'm connecting to my Raspberry Pi, which is Linux/ARM. So this is 32-bit Linux operating system, still running Docker. The Docker API is exactly the same. So even though this is an older version, that's not a problem. The Docker server that's running on my Pi, I can control that from my local machine. And I can do the same thing. I can run exactly the same command that I ran on my Windows container, Docker container run with that image name. It's a little bit slower because the 32-bit ARM is a bit slower than my super highly powered Windows machine, but I get the similar output. I get hello from chapter 2, I get the container host name, I get the operating system, which is Linux and ARM v7, so that's the 32-bit code name, and then the IP address. So this is working in the same way. The app runs in the same way. I get different output because the output is platform dependent, but it works in the same way. And if I inspect the image using that same command, then I see I've got the Linux ARM image. So just to hammer the point home, Docker, when you pull an image down, Docker uses the OS and architecture on the engine that you're running Docker on, and it pulls down the matching architecture if it's a multi-arch image. If this wasn't a multi-arch image, it just wouldn't work if I tried to run it. If it was built to run on Linux on ARM, then I just couldn't run it on Windows. And just to be entirely sure, I will run my Pine 64, which is 1, I think. There we go. So this is a 64-bit ARM machine. Again, Docker's installed. This is Linux ARM 64. I can run the exact same commands. So let's go and grab that Docker run. So, oh, it hasn't got the image. Excellent. So we'll see this one pulled down. So this is pulling down the image. This is the kind of generic image name. And in behind that, there are the variations for the different versions that I've got published. So it's going to download the image first, and then it's going to run the container, which will just show me that script again. Any second now. When I did my dry run, I must have picked a different machine. I've got 7 of these Pine 64s lying around. I must have picked a different one earlier. Well, while that's running, I will skip to the next thing, and I will show you how that container image looks in Docker Hub. So this is the image that's been pushed to Docker Hub. So if I do that Docker container run and give it this image name, or if I do a Docker image pull and pull this image name, if I use the latest tag is only one tag, but actually in behind there are 4 different versions of this image. And Docker Hub does a really good job of telling me how what I've got available here. So the idea of a multi-arch image is a part of the Docker registry spec. So whichever registry you're using, you can support this, but Docker Hub does a particularly good job of showing you what's available and showing you all the different images. Okay, let's see if that's run. Oh yeah, there we go. So on my 64-bit machine, I get some random container ID. I get the name of the ARch64 is a variation of the ARM64 name. And if I go ahead and do my inspect here, we'll see that Docker pulled down the right version of that image to get me my container. Now, there are a couple of command line ways to look at those container images that are available for a multi-arch as well. So there's this Docker manifest inspect. So the idea of a multi-arch image, and I've got a diagram showing you this in just a second, is the thing that has the thing that is the kind of grouping, the image name that has all these different variations behind it, you create that with a manifest, and you say this image called diamol CH02. Actually, in behind that, there's a Linux variant for ARM64 and one for ARM32 and one for Windows and all that sort of stuff. That's called a manifest, and you can inspect the manifest that's on a registry. So if I run docker manifest inspect, this makes a few calls up to Docker Hub. It looks at what's available and it goes and gets the unique IDs for each image. So it takes a few seconds and then it's going to push me out all the information about all the variants of this image. So I've got my Windows version, my Linux ARM and ARM64 and all those things. So this tells me a lot of detail. This is the specific image ID. So if I wanted to, I could go and pull it by its SHA instead of the image tag. But it tells me the architecture, and for Windows, it also tells me the OS version. Windows has a slightly different way of dealing with versions than Linux does. Okay, so that's the first demo, just to show you how all this stuff looks. And let's go back to my slides. Okay, so as a consumer, like that's pretty straightforward. All I need is to know the name of the image and I just do Docker container run. And provided whoever's publishing that image has produced a variant that's going to work on the machine that I'm trying to run it on, then it's all transparent to me. And lots of image publishers are doing this, particularly the official images on Docker Hub. So if you go and look at something like Postgres, there are variants of the Postgres image for all the variations that I've been talking about: Linux on Intel and ARM32 and ARM64, the Go language, .NET Core, Java. They all have multi-arc images that you can use to build your own multi-arc images. So it's been established for a little while, but it used to be a little bit tricky to do, which is what I'm going to show you now. So the old way of doing this, if you want to build a multi-arc image, is you need multiple architectures. So you need to have physical or virtual devices that you've got control of that all have Docker installed on them for all the variations that you want to support. So if I want to support Linux ARM32 and ARM64 and AMD64, then I need one of each of those machines. And if I want to support Windows AMD64, then I need a Windows machine too. They all have Docker installed. And then when I build my image, I'm going to do a Docker image build command, and I'm going to do one at a time. So I'll send to each machine, go and build the image, and it will build me the Linux ARM64 version. And the next machine will build me the Linux ARM32 version. Now so you've kind of got a build farm, except that it isn't, because it's just a bunch of machines that run Docker and you're sending them individual commands. So you might have something orchestrating that, which in this case would just be something like Jenkins, which I'll show you my Jenkins setup in a second, which is going to make sure you go and build all those things. But they're not a farm that you can kind of dispatch a whole bunch of things to at one time. And the other disadvantage is that those Docker files that you're passing to each machine, they might be different. So you might end up with a situation that there are platform differences in the application that you want to build, or in the images that you're using as your base image, so that you have to have a different Docker file for each architecture. So I've got Dockerfile.Windows, Dockerfile.ARM64. And so the disadvantage of that is you end up with all these Docker files that proliferate. So then what people do is they create a Dockerfile template and they have an automation to spit out the real Docker files and then push those onto the build servers, and it just gets kind of clunky. But this is what people have been doing for ever since multi-arc images were around. So what happens here is I've now got a bunch of images, one on each machine, which has been built for the Docker file that was given. They may all be the same application, but Docker has no concept of that. So then I push them all to my hub. So I push them to Docker Hub or whatever registry I'm using. And again, it's one at a time. I'm connecting to each of those machines. I don't have this notion of a consolidated build farm that I'm just telling to go and push that image. I'm going one at a time to push up each flavor of the image to Docker Hub. And then when I go and look at Docker Hub, I'm going to have 4 separate images, which aren't related in any way until I build that manifest, which is what makes them a multi-arc image. So step 1 is to build all the images on different machines. Step 2 is to push those different images up to Docker Hub or your Docker registry. And then step 3 is to create the manifest. So what the manifest does is it's a list of the image variants that are available. So in this case, I've got 4 variants of my image for the two ARM architectures that I support, 32 and 64-bit, for Linux and Windows on Intel. So I've got 4 variations. I create a manifest that lists those 4 variations, and then I push that manifest to the hub. So the manifest is something that lives in the registry, just like the images live in the registry. And now I've got this concept of a multi-arc image, because on the left-hand side of this diagram, I have an image called my app, which works for several OSs and several architectures. And on the right-hand side, I've got for each one, the image name has a specific tag. So I've got my app : Linux ARM and my app : Windows AMD 64. So those are the actual images that live in Hub, but I've got the manifest which puts them all together as a single multi-arc image. Okay, and then this is what enables the end user to just use that multi-arc image name. So they don't have to say, oh, I'm running on a Raspberry Pi, so I need to go and find out the tag for the Linux ARM variant, because they're just going to use Docker image pull or Docker container run my app. And then between the Docker engine and the Docker registry, they'll work out which is the right version of the image to send down and where the container is going to run from. Okay, so like I said, it's a little bit clunky. You've been able to do this for the longest time, actually, but there are a few steps involved. So I won't go through them all tortuously, but I will show you what my setup looks like. So if I go here, let's get rid of that for a second. So in order to build all the images that I'm working on for this book, this is my Jenkins setup. So I've got Jenkins running on my Docker swarm. So my swarm has half a dozen nodes, and there's a whole mixture of architectures in there. When I want to, for each of the samples or the exercises that I go through in the chapters, there's a Jenkins job to build from the Docker files and make sure everything's up to date. So here's an example of something that I think is it's a Go application. Let me just go and click on configure. And this is what it looks like. There's a whole bunch of stuff here. If you're not familiar with Jenkins, don't worry, because I'm just going to go and look at the bash script that actually gets executed. And this is going and looping through each of my build servers like I did in the diagram. So there's a little loop here that says, I'm going to go and fetch an IP address for one of my ARM 32-bit workers. I'm going to get an IP address for one of my 64-bit ARM workers, and for my Intel Linux and my Windows Intel. And so I end up with all these IP addresses, and then I say for each one, go and build the Linux ARM variant, the Linux ARM 64 variant, etc., etc. And then the build script just connects to the Docker host for the IP address. They're all been TLS secured, so the certs and everything come from Jenkins, and then it just does an image build, and it tags it with the name of the job, which is the image name, and then the tag for the OS and the architecture. So at the end of this, I'm going to have 4 images that have been built, one on each of my build machines, which are the nodes in my swarm, and then I go and push them all. And the push stage, just again, it connects to the Docker host, it logs into Docker Hub to make sure that I'm logged into push, and then it does a Docker image push. So at the end of this stage of the build, I've now got 4 separate images in Docker Hub that aren't kind of linked in any way. So then the build goes on to do the manifest part. And so it does the manifest create, and it lists out all the variations which I'm supporting, which are now up in Docker Hub. So the manifest connects to the registry to build up the list of things that are going to be the multi-arc image. And then just for debugging purposes, so I can see in the logs, I do a Docker manifest inspect to make sure everything's as it should be, and then I log in and do the manifest push. So that's going to give me the grouping mechanism for the image name with all the tags in behind that. And if I go and look at an example of one of these builds, let me see if I can find one that didn't fail. It's been a while since they failed. So my console output, you'll see there's a whole bunch of stuff in here. Things like it's getting the IP addresses for my nodes, so they're the machines in my swarm, and then it's doing the build. So I can see this is the Dockerfile instructions running through, and then ultimately down here it does the push. So these are all the separate images. So there's the ARM64 being pushed to Docker Hub, and there's the Linux AMD 64, and then finally it comes and it builds the manifest. So the manifest includes all those variations, and then it does the push. So it pushes the manifest, which means now this CH04 image gallery is a multi-arc image. I've got a link here so I can see what they look like. And that's now a multi-arc image that's got all the separate individual tags, but it also has my overall tag that has the multi-arc in here. Okay, so like I said, you could do it, but it's a little bit awkward. Now, the advantage of the older way of doing things by building the individual images and writing the manifest that groups them all together, the advantage of that is you can have different application contents in each image. So actually, you can only really do a multi-arc image with one Docker file and one set of source if you're building a cross-platform application. So you can do that with Java, you can do that with Go and .NET Core and that sort of stuff. But in some cases, there are variations between the images for the different platforms. And in order to support that, you need to have separate Docker files. So as an example of that, if I go and look at my source code here, the one I've just shown you is this Go application. Really simple bit of Go. I'm no Go programmer. All this does is what's this? Is like an API, a REST API. Oh no, it's some sort of web page. And then there's a Docker file for this, and it's a multi-stage Docker file. So this is the kind of best practice that we've been talking about Docker for a while now. So you have your multi-stage Docker file that has part one is compiling your application from source. So in this case, I'm using a Golang SDK, which is, again, this is something that I own, but this is based on the official hub image that has Go in it. Copy in my source code and do a build. And then the final stage, which is packaging my application, packages up a bunch of default configuration, sets up the entry point command, and then copies the built output from the earlier stage. Now, this is a cross-platform Docker file. I can run this on a Windows machine and I'll get a Windows image out. I can run it on a Linux machine and I'll get a Linux image out. And because the base images are all multi-arch anyway, that will flow through. So if I run a Docker build command on a Raspberry Pi, I'll get a Raspberry Pi image out. But some of them are a bit more complicated than that. So if I look at Maven, so there's a Maven image which is used for building Java applications. There are Maven images on Docker Hub already. So if I look at for Linux, my Docker file for Linux is just using the official Maven image because that gives me everything I need for Linux AMD 64 and for Linux ARM 64. But there is no variant in the official image for ARM 32. Now I want to build a Maven image that I can use on Windows, Linux, Raspberry Pi. So I need ARM 32 in there as well. So I have a separate Docker file for ARM 32, which uses some other person's image, which I've been through and checked and all looks good. So when I start to build these things together, I'm using different base images to build my own image, but ultimately I will have an image called diamol/Maven, which will work on any machine. Whereas if I use the official image, I wouldn't be able to use that on a Raspberry Pi. And then the other variant is Windows, for which there is no official image that has Maven in there. So I've got, this is a proper Docker file that does all the install for me. Again, it's a multi-stage build. So the first stage is doing the download of Maven, and then the second stage is based on the OpenJDK. So I've got all the Java JDK, and then it copies in all the Maven stuff from the earlier stage. So when I build all this with my build job in Jenkins, which looks very similar to the previous one, but I'm using different Docker files for the different platforms that I want to support. And that individual step of having separate build servers that you connect to and pass them a Docker file and get the image out, and then build the manifest around it, that enables you to do this, to support the fact that what's going into each image is different for each platform. Okay, so let's go back here. Okay, so that's great if you do need to be able to support that, but and if you're an image author who's providing images for other people to use to base their images off, then you're probably going to need to get down to that sort of level at some point. So the images that I've got in that source code for Diamol, there's a whole bunch of stuff going on for different levels of application that I'm building. But if you're just an application builder writing some Go applications or some Java or some Node.js, and you want to wrap them up in containers, you probably don't need to go that far, because you probably don't need to be able to say, when I'm packaging for Windows, do this step, and when I'm packaging for the Raspberry Pi, do this step. You ideally want to have one set of source code, one Docker file, and just build it relevant for each platform. That's what Buildx lets you do. So Buildx is a new component in Docker. It's been the thing that powers it is a component called BuildKit, which has been around for a while. So actually the heritage of Buildx is pretty secure. It's been around for a long time, doing some good stuff. It's recently come into Docker Desktop. So on Docker Desktop for Mac or Windows, if you're on the Edge channel, you've already got Buildx. If you haven't got that, then you can add it separately through for Docker Community on Linux as a separate add-in. What Buildx does, it does two things. So firstly, it lets you build a Docker image that is native to the machine you're building on, just like Docker Build does. But it also supports emulation. So I can go and on my Intel machine, I can build an image targeted for Raspberry Pi. So on my Mac, I can build an image, target it for the Raspberry Pi, push it to Docker Hub, and then on my actual Raspberry Pi, I can run that image. And the advantage of that is, well, It may be quicker to do it on the emulator than on the actual device if it's a low-powered device. It's useful for just being able to have a loop where I'm building and testing the things on the device without having to keep connecting to the device, do a Docker build, blah, blah, blah. So I can push that out really, really quickly. The other thing that you can do with Buildx is you can build a genuine build farm. So I can use exactly the same machines that I've got currently, but rather than connect to them independently and do a Docker image build and pass them a Dockerfile, and then write my Docker manifest and push that up to the hub, I can use Docker Buildx to create this build farm, which operates like a build farm. So all I do when I've got that established is I do a Docker Buildx build, and I pass it a single Docker file, and it parallelizes that, and it pushes out to all the machines in the build farm and tells them to build. Now, ultimately, this is going to give me a native build from each builder in the farm. So my Raspberry Pi will get me a Raspberry Pi image, and my Windows machine will get me a Windows image. But then Docker Buildx will build the manifest for me. So at the output of this command, because I've got 2 extra parameters, the -- platform is listing all the platforms that I want to support from this build, and then Docker Buildx will go to each of these elements in the build farm and give them the right platform to build. And the -- push says, when you've built all the images, push the whole thing to my registry. So in this case, it's going to be Docker Hub. So it's going to build them all independently on those machines and then push them to Docker Hub, build the manifest, push that. So I'm going to get a multi-arc image that I can use anywhere from a single command. So Buildx is a really, really nice way of doing this sort of stuff. So let me show you the demo for this. Okay, so in here, so I'm going to connect to a separate machine where I've got Docker Edge running. So this is a Windows machine. I've got Docker Desktop. The Edge, this is the latest Edge version, so it's 1903.2. I'm running in Linux containers mode at the moment. That's not a requirement, I just happen to be doing that. So what I can do here, let me get my cheat sheet back and drag that out of the view. So I can do, let me go to the right place, make sure I'm in the right place. Okay, cool. So if I do a Docker Buildx ls, so Docker has this notion of builders, which may be a farm of several builders, or it might just be one machine. So Docker Buildx ls is giving me all the things that I've already set up. And the default is just to use my local Docker instance. I've got a whole bunch of other machines that I've already configured as a build farm, and that's my webinar build farm, and I will use those in just a second. But to start off with, I'm going to show you how that emulation works. So if I do have a look at the Docker file that I've got here, this is a .NET Core application. So this is exactly the same principle. It's a multi-stage build. So stage 1 uses an SDK image, copies in all the source code. It does a .NET Restore, which if you're not familiar with .NET Core, that's just bringing in all the dependencies for the application, copies in the rest of the source code and does a publish. So when this stage is finished, I've got my built application with all the dependencies ready to run. The second stage is built on a runtime image. So this doesn't have the SDK. This just has the bare minimum that you need to run your application. And this just copies in the application from the builder stage and sets up a volume for the data. This is a stateful application. Okay, so it's all fairly simple. Now I could build this with a Docker image build, but seeing as I'm using Buildx, I'm going to make sure that I'm using the default builder. So when you install Docker Desktop, the Edge version, you'll only have one builder, which will be your local instance. To add more builders, you need to run a few more commands that I'll show you in a second. So I'm using my local builder, and I'm going to do, let's copy that command in. So this is an Intel machine, but I can do Docker Buildx build tag. So it takes the same format as Docker image build. So it takes a tag for the output image. So I'm going to call this to do webinar, but I can target it to run on ARM64. So this is not an ARM machine. This is going to use emulation. But when it's using the emulation, even though it's using QEMU behind the scenes, which is an open source project to emulate different CPU architectures, all the caching that you get from Docker build you still get that with Docker Buildx. So I've already run this, so the cache happens super quickly, and this is up and running and ready to go now. So now I've got an image locally called 6i to do webinar. Let me just check that it is there. So I'll do a Docker image list. And there's my ARM64 version. There's the cache, so it was already built a few hours ago. So that's going to be targeted for ARM64, which I can check if I do Docker image inspect. And that should show me, amongst all the other bits and pieces that are in here. There we go. So the architecture, oh, I moved around. The architecture is ARM64 and the OS is Linux. So even though this is not an ARM machine, I've built something that I can push to Docker Hub and I can run that on a Raspberry Pi 4, which is 64-bit ARM processor, or a Pine 64 or a Rock 64 or whatever it is that I'm using. Okay, so that's pretty cool, and I can cut out the fact of having to have a physical board if I want to build for something. If I want to test some stuff out that's going to run on some IoT devices, I don't need to have one of each type of device. I can emulate that, push that up to a registry, and then get the devices to pull stuff down. But it gets much more interesting when you do the kind of build farm approach. So I've already done this. Let me bring this over here. So what I did to put together my build farm was this docker buildx create command, which means create me a builder and use one of the machines that I've already got registered. So my Pi 3, and then I added in with the append command my Pine 64, and then I added in a Linux Intel machine. So this is how I build up my build farm, just a couple of simple commands. And I can do that because I already have those machines listed as Docker context. So if I do Docker context list, if you haven't used that, it's a really nice way of managing other machines. So you can do a Docker context add and say, here's my Raspberry Pi, that's where you're going to connect to it. And then you can just switch in between the two. And Docker Buildx works with Docker context. So I can just add those machines to make my build farm. So if I do a Docker Buildx list, it's going to show me all my build engines. And one of them is going to be that webinar build farm. There we go. And so if I do a Docker Buildx use, that's now switched to the current builder. And now I can build multiple platforms, build to target multiple platforms from a single command. Because my machines here, my build farm has got support for 32-bit ARM, 64-bit ARM, and 64-bit Intel, and even through Intel 386. So I can tell with this single command, I want to build an image. I'm in the same folder, the same Dockerfile. I'm targeting it as my buildx tag, and then there are multiple platforms that I want to build. So I want to build them all in one go. And if I do the -- push, then this will also push up to Docker Hub. So this is going to go and connect to all of the machines. You'll see the output from Buildx is different from Docker build. It breaks everything up into small steps, and it tries to do them all in parallel, and it goes as far as it can. But the cache is still existent. So I've already had this build farm set up. I've already run through these builds. So we should see that each of the steps comes from the cache, but it just takes a little while to go and connect to all those different machines and then find out that you've got the cache, and then ultimately we'll get there. You'll see at the top here, this is step 43 of 43, and at the moment it's exporting the layers. So it's taking the built image and getting them ready to push them up to Docker Hub. Okay, so we'll let that roll on, make sure it really is coming from the cache. Okay, cool. And if nothing else, then Docker Buildx is really impressive to have running on your machine if somebody's looking over your shoulder. Because if you start with an empty cache, you just get these millions of lines coming through. It makes it look like you're working super hard. Okay, so let's let that finish off. What I'm going to do, I've already pushed this from a previous build, so I should, on a completely separate machine, be able to do a Docker manifest inspect. And look at my Buildx images. And again, this goes up to Docker Hub and it checks all the SHAs, so it takes a little while. And there's the output from running that command earlier. So I've got my Linux ARM64, my ARM 32-bit, my AMD 64, all from that single command, all managing that build farm in a really neat, efficient way. So I don't have to go and do all the stuff I had to do before of finding an IP address, connecting to that machine, sending it the Dockerfile, getting the image, doing the push, and then building the manifest. Buildx does the whole thing for me in one go. Let's see this. Oh yeah, so it's finished. So that was super quick and it's all done. So Buildx is the new evolution for doing this. Okay. How are we doing for time? Oh, excellent. Okay, so there's a couple of things that's it for the demos. There's a bunch of questions coming in, so we'll get to as many of those as we can. There's a couple of things that's really important to take away from this. Everything should be multi-platform. So any app that you're building now or any app that you're evolving, you should look at, is this multi-platform? Have I got the opportunity to run this on a low-powered, low-cost ARM processor in the future without rewriting all my code? And if the answer is no, then that should be added to your backlog, in my opinion. So if you're running on .NET Framework, then you move to .NET Core. If you're using Go or Node.js or Java, then you're already there. So that's good stuff. even if you're not doing this now, the ability to do that in the future without a project to rewrite all your code is super important. So as I said, AWS support ARM instances for virtual machines. There's Packet and a couple of other providers that do the same. And as this thing gets more and more competitive, then other clouds will presumably offer the same thing. And the ability to just say, I've already got my Dockerfile, I've got my source code, I can run a Docker Buildx command to target ARM64, run this thing in an AWS A1 instance, do all my automated tests against it, and if they all pass, then we just migrate everything to ARM. So if all your apps are multi-platform, when you decide to make that decision, there's nothing to do other than to run your tests and do your load tests. Always use multi-stage Dockerfile. So multi-stage Dockerfiles have been around for almost 3 years now. And if you've been kind of following our best practices, then you already can do what I've just described. So if you have a multi-stage Dockerfile where stage 1 is the SDK, and that's using an official image or a derivation of an official image, and then the final part is packaging your application up, and again, that uses an official image, then those official images are already multi-platform, so you should be able to just build and target ARM without having to do any work, not changing your Dockerfile or your source code. So multi-stage Dockerfiles, multi-platform application frameworks are going to get you the freedom to kind of run this stuff anywhere. So a couple of things, Buildx is in experimental at the moment, so you'll get it from the Edge channel, but it's been based on BuildKit, which has been around for a couple of years. So actually it's on this, it's a solid foundation. It's just experimental at the moment because things are liable to change. The alternative is to do the earlier workflow that I showed you of having a build farm that you manually manage and connect to each, do a Docker build, and then push those images and then build the manifest. The manifest command is also experimental, but that's only because that's a CLI tool. So that's been added to the CLI. You opt in to use that, and then you've got manifest inspect, manifest create, all those other things. Okay, and for the links for this stuff, all the demos I've walked through, they're up on GitHub together with all the source code. That's that ISGD link at the start. I've mentioned a couple of times that I'm writing this book, Learn Docker in a Month of Lunches. Manning of the authors, the publishers, they have this thing where you can subscribe to the book while it's being written. So you can go and buy it now and get the first 5 chapters, which is all I've had time to do. But as I finish each new chapter, you get that and all that sort of stuff. There's a 40% discount code there if you're interested in that. If none of what I've said has made any sense at all, then if you're a Pluralsight subscriber, there's a whole Docker learning path with a bunch of Docker videos from Docker captains like Nigel Poulton, from people like me, that will take you from 0 all the way through to being a Docker and Kubernetes master. And if you're interested in coming to the container conference for the industry, then DockerCon next year is in Austin in Texas, and that's going to be in June. So that's kind of it for the slides. I'll leave that one up so you can make a note of all your bits and pieces. Okay, and let's see what we've got in the way of questions. I'm not sure if I can see the questions. So there was a question about, is this being recorded? And the answer is yes. Let's see, any technical questions?
Yeah, which Raspberry Pi were you using? The 4? It would be good to understand the minimum requirements running Docker on an embedded system.
Wait, where did you see that question? I can't see any questions.
I don't know. Maybe click show answered questions.
Okay, hang on. So let me. So tell me again. Which version of Raspberry Pi was I using? I was using a Raspberry Pi 3. Good, practicing with the muted button. So I was using a Raspberry Pi 3. You can use the Raspberry Pi 4. Mine is not plugged in, as you can see. In terms of going back, it's really the versions of ARM that are supported, and the ARM version codes are a bit elaborate. We go back to V6 at least, I think. So you can run this stuff on. I think you can run this on the earliest Model B Pis, I think.
Okay, and then next question, do other repositories such as Nexus support multi-arc Docker images in the same way as Docker Hub?
So if they support the registry version 2 API, which I think everything does because that's what it's all kind of based on, then yes, so they should be able to do the manifest push command. That's how you're going to find out if they support it. And if not, then it's a choice of the registry publisher if they're going to support multi-arc images. It's not a Docker Hub only thing. It's part of the registry spec. So they should at least allow you to push manifest, which is how you get the multi-arc, or inspect manifest. Whether they surface it in a friendly way like Docker Hub does, I'm not sure. That would depend on the implementation. But yeah, you should be able to store variants in that same way.
And then we had a question asking for the Git repository of the demo, and I think that is the first bullet on your slide.
Yes, that's that link there. So hang on, let me just prove that that actually does do something. So
we believe you. You don't have to prove it.
Well, this might be copied from some other presentation with something else on it. So
and maybe you could put that in the chat.
Yeah, sure.
To do.
There you are. You see, that's something completely different. Yeah, how has that happened? I see. I've only copied part of it. I will put the whole thing in the chat, and I'll just verify that it really does work. I could have gone badly. There could have been anything that I linked to there. There we go. Okay. Let me put the full thing in the chat.
Thank you.
Okay, there we go.
All right, next question. If we build for an ARM platform, can the application in the Docker container access GPU function in the ARM processor?
It depends on the version of Docker that you've got and the architecture and the support that it offers you. So if you are following, there's a Docker captain who's doing a lot of this stuff right now, and he's the person to check out. Let me go and find. He was blogging about this lately. It's fantastic. If you've got the Jetson Nano, which is an ARM processor with the super NVIDIA GPU bolted on, then you can run Docker on that. You can put it into a swarm, and you can direct traffic to that. It does depend on the hardware and the support that you've got, but yes, you should be able to do it. Let me find you. I'll put another link in there when I find out what this stuff looks like. So Ajit's been doing some really good stuff here.
Yes, I think we're gonna ask Ajit to come do a virtual meetup as well.
Yeah, definitely. Yeah, he's been doing some interesting stuff with like collecting. He's been doing image recognition on the device, and that device is a Jetson, I think. So let me try. I can't find his tweet at the moment. Let me find that. So do you want to fire on the next question? I'll put that in the chat.
Yeah, and I can look for that too. Okay, next question. How can I configure a Linux host to build, run multi-arc images as seamless as Docker Desktop? Okay.
So you're asking Docker Community Edition?
QEMU bin format _misc is installed configured. Currently, containers need the QEMU static binaries mounted as a host volume or included in the image to avoid the file not found error. And Docker Buildx create only shows the host architecture and not the other available architectures.
Yes, so Docker Buildx can work with different builders, but the emulation is only packaged with Docker Desktop. So if you're running on Mac or Windows and you've got Docker Desktop on Edge, then you get QEMU as well. So QEMU comes bundled with it. If you have a separate QEMU, then you have to kind of cobble it together yourself. And I've not done that myself. It depends on what you're trying to achieve, but the QEMU stuff is really useful if you're a developer and you're working on a laptop and you just want to get something built and try it out on a device. If you're actually building stuff to run in production, you're better off having a farm of actual devices and then managing them with Buildx. So remember, Buildx does those two things. It does the emulation if you have the QEMU set up, but it also controls your farm of physical devices. If you're not just trying stuff out, then you're going to want to get to the point of having actual devices. And I say physical; it doesn't have to be physical. You can spin up an A1 instance in Azure, in AWS, and that can be part of your Buildx farm. So, short answer: I'm not sure how you configure that in Community Edition. All the BuildKit stuff is there. There's nothing that isn't open source. You should be able to piece it together. But think about where you're going, because if you do want to build stuff that you're going to ship to a registry and have people run on machines, you're going to be better off having a farm of physical or virtual devices.
Okay, next question. Right now, is it common practice to use Docker Compose with Linux and Windows non-cross-platform images combined on Docker Desktop, or is it still in experimental phase?
I'm not entirely sure what the question's asking there. So Docker Compose, with Docker Compose, when you're specifying your service images, then the image is just your image reference. If that's a multi-arc image, then when you do a Docker Compose up, it will pull the relevant image for your architecture, same as always. I'm not entirely sure. You'd have to. So if I'm not answering your questions properly, then feel free to ping me, because I'm just I'm elton@docker.com. By email, or just at Elton Stoneman at Twitter. So if I haven't answered you, then get hold of me that way. But yeah, there's nothing specific about Docker Compose that stops it working with multi-arc images. So it's just a question of whether the images that you're using are already multi-arc. And the same with building through Docker Compose. So in your Docker Compose file, if you have a build line that tells Docker Compose where to find the Dockerfile, if that Dockerfile is using multi-arc images for the stages, exactly the same thing. So Docker Compose will just use whatever the current architecture is.
All right, next question. Are there significant performance detriments to running Docker containers on embedded hardware such as ARM?
There's no additional performance problem in running in containers as opposed to running natively. So bear in mind that these devices are more limited than most desktop or virtual machine devices that you get in the cloud. So like a 32-bit machine, if you connect to a 32-bit Raspberry Pi and you do a Docker build, then it's slower. Like the network connection is slower, the build times are slower. The run of a compiled application should be fine depending on the load you're putting through, but the build times are slower because they are not as performant CPUs. But the trade-off for that is they are so super efficient, and you can run so many of them with such a limited amount of resources in terms of electricity and heat and that sort of stuff. So yes, there is a performance hit in moving to your ARM architecture, depending on what architecture it is, but using containers doesn't add to that. And if you look at the what Amazon have done with their A1 instances, they basically categorize the types of app they think are suitable for their ARM64 architectures, and it's like most apps. So it's not like super CPU efficient, CPU dependent stuff, but things like web applications where load is variable, APIs, all that sort of stuff. Then yeah, absolutely, you can just do that. And the benefit of having something like Buildx and multi-arc images is that it's super easy to test that stuff out. So without hardly, you can put aside a day of effort to build your application, target ARM64, spin up an A1 instance, do a bunch of load testing against it, and say, actually, we're currently running 50 VMs, 50 Intel VMs. We could do the same application with 30 ARM VMs.
All right, can Buildx be used with Docker Compose?
Don't know. So you can set Buildx to be the default Docker build command, but Docker Compose itself, I'm not sure whether it sends commands direct to the API. I think it might send direct to the API. So I don't know is the answer to that one. Sorry.
And when will this be supported on Linux? I've installed Buildx, but can't get it to fully work.
So in theory, it is supported on Linux. There isn't a bundled package for Docker Desktop for Linux like there is with Mac and Windows. So you are putting the pieces together yourself. But yeah, it should be documented. If it doesn't work, then yeah, they'll file an issue and we can kind of get that looked at. Not me, but somebody can.
All right, and you mentioned QEMU for emulation. What platforms is that available on?
So QEMU emulates all sorts of stuff. The way we use it, I think, actually, if I go back to here, it will tell you. So Docker build list. So the QEMU that we bundle with Docker Desktop isn't like the full thing, but you can see from this list here that it's all the Linuxes. So AMD and ARMs, 32-bit and 64-bit. The IBM. Like the mid-range and the big IBM servers are in there too, and then and then i36. So kind of all the major stuff. So QEMU does emulation. The full QEMU project emulates all sorts of weird stuff, but Docker isn't supported on all those weird things. So in theory, I think we bundle QEMU with all the supported Docker deployments.
All right, and do you have any insight on what the roadmap looks like for Docker on ARM for platforms other than the Raspberry Pi?
So platforms other than the Raspberry Pi, I mean, it's I only mention the Raspberry Pi because it's the most popular. I have one Raspberry Pi and I have 10 other things. So the roadmap is it's built for a particular ARM chip, and so ARM64 and ARM32. I've been running them on these Pi and 64 boards. As long as they're kind of standard ARM v7s and ARM v8s, then it should just work. The operating system that I use on my machines is called Diet Pi, which doesn't have a UI, because why would you have a UI for these things? And this supports like dozens of different devices. It tells you which devices it supports it for. So all I do when I'm onboarding a new device is I download Diet Pi, and then I run the get.docker script, get.docker.com, and see if it works. And it's worked on everything so far.
All right. To expand on the question about support for this feature in different registries, would that support also be extended to private internal registries? How difficult would that be to implement, assuming it's not off-the-shelf functionality?
So if you're talking about the Docker open source registry, so which is on GitHub as I think it's called distribution, then I think it's supported in there. I haven't tried it. I should try it actually to make sure that's true. But yeah, it's just part of the registry spec, and that open source implementation is the registry spec. So you shouldn't have to do anything to make that work.
All right, we have seen a lot of activity recently around RISC-V in the open source community. Am I saying it wrong?
Yeah, RISC-V.
RISC-V, oh, there we go. All right, will RISC-V CPU architecture also become supported by Docker?
We would definitely want to, yeah, absolutely. So among the other activities, you'll see Justin McCormack, who is one of our Docker engineers. He's heavily involved in that. He's interested in that space, and a bunch of other people are. So yeah, I mean, it depends on as it does with everything else, it depends on the amount of effort involved to support it, and the amount of the priority list within the projects that we have. But there's definitely an appetite to support it, yeah.
All right, we are on to our last question and our last minute. So what are some of the caveats of moving an application from one architecture to another?
You will very quickly find out if you're using weird features in your application platform. So in theory, you should be able to, so as an example, like SQLite, if you were using an embedded database in SQLite, the way you package that up, you're going to be packaging up platform-specific version of SQLite. So if as part of your packaging, you are not able to go and say, get me the SQLite for wherever I should be packaging it up for, you're going to find you're packaging a 64-bit Intel SQLite, and when you try to run your application, it's just going to fail. And any kind of nuance along those lines. More clear example is if you want to move from Windows to Linux, and you're making assumptions about the platform. That's what's going to hit you. It's not going to be the performance, because you can test that really quickly. It's not going to be the availability, because again, that should all be stuff that you can get to bottom with really quickly, and people have done before. What's going to get you is that some assumption was made about I'm only ever going to run my app on one platform. So classic example, I'm building for Windows. I'm going to assume that I can get access to the C drive, and all the paths in my application start at C:// rather than using the platform independent versions. And that's just going to fail as soon as you try to run it on Linux. So yes, there will be performance differences, but you can quantify them very quickly. What will get you is that somebody made an assumption somewhere in your development stack that that it's just going to fail in a different environment.
All right. Thank you so much, Elton, and thank you so much to everyone who joined this meetup and the fabulous questions and discussions. As I mentioned, this was recorded, and we will be sending out a link to the recording.
Cool.
So thanks. We'll be posting our next virtual meetup soon as well. So hope to see you then.
Thanks, Jenny.
Bye.